Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 71st video class of DIP, we will study regional descriptors in image description for digital image processing and its implementation in MATLAB. We learned boundary descriptors in the previous video class, and in this video class we will learn regional descriptors. Starting with the name, what is the meaning of regional descriptors? As the name suggests, regional descriptors are one that describes the regions. For example, what is the area of the region, what is rectangularity ratio, what is compactness, what is circularity ratio of that particular region. Okay, and of course these regional descriptors will be also implementing in MATLAB. Okay, so let us start. We are learning image representation and description, and this image representation and description is very important before feature extraction or object recognition. So the regional descriptors can be broadly classified into three types: simple descriptors such as area, perimeter, compactness, etc. Topological descriptors which measure the shape structure without changing by deformations, and textures which provides measures of smoothness, coarseness and regularity. And in textures also there are three approaches: statistical approach, structural approach and spectral approach. And see, regional descriptors are dealing with regions as opposed to boundary descriptors that deals with boundaries. Okay, let us first understand simple regional descriptors. First simple regional descriptor is area. The number of pixels in the region defines its area. For example, this is our object, then the total number of pixels in this object will define its area. For example, here the area will be 55. Next is perimeter. Perimeter is the number of pixels in the boundary of the shape, and we have already learned this perimeter in our previous video class of boundary descriptors. So for this image, the perimeter will be 25. The next is compactness, which is also known as circularity. It defines how closely packed the shape is. It is the ratio of perimeter square upon area, and the most compact shape is a circle, which is 4 pi. For the circle, the perimeter is 2 pi r. So perimeter square is 2 pi r whole square upon area is pi r square, which will give 4 pi. All other shapes have a compactness larger than 4 pi. So compactness is equal to perimeter square upon area. So for this object, from here we know that the perimeter is 25. So 25 square upon area is 55, which is equal to 11.36. Next is the circularity ratio. It is the ratio of area of the region to the area of the circle having the same perimeter. So perimeter is same. Okay, so the area of the circle with perimeter length p is p square upon 4 pi. Then the circularity ratio is given by this equation. Let us first understand how this area of a circle with perimeter p is p square by 4 pi. Okay, see, the perimeter of a circle p is equal to 2 pi r. So if we square on both the sides, we get, so I can write this equation like this: 4 pi into pi r square. Why I am taking out pi r square? Because we know that pi r square is the area of the circle, right? And therefore the area A is equal to perimeter square upon 4 pi, and that is what is written here. The area of a circle with perimeter length p is p square upon 4 pi. Okay, now let us understand how this equation comes. See, in the definition it is given that circularity ratio RC is the ratio of area of the region to the area of the circle, right? So the area of the region is A upon the area of the circle, which we have found out is p square or perimeter square upon 4 pi. So therefore circularity ratio is equal to, the denominator of the denominator will go to the numerator, which is this equation. Next is the rectangularity. It is defined as the ratio of area of the region to the area of bounding rectangle. Suppose this is our region, this ellipse, and this is the bounding rectangle, and say the area of this ellipse is A and area of this bounding rectangle is say B. Then rectangularity R is equal to A upon B. That is the area of the region to the area of the bounding rectangle. Next and last simple regional descriptor is the elongatedness. It is the ratio between the length and width of the minimum bounding rectangle of the region. Say our region is this ellipse, and this is the minimum bounding rectangle of this ellipse, and for this rectangle this is the width W and this is the length L. Then elongatedness E is equal to the ratio between length and width, that is L upon W. Next regional descriptor is the topological descriptor. Topology means the study of properties of a figure that are unaffected by deformation. So topology consists of two words. Topo means locality and logy means study. That means study of local structure of any shape. And the topological descriptors are features that describe the properties of a shape or a region in an image that are invariant to deformation, such as stretching, bending or twisting, as long as the shape or region is not torn or joined. For example, the rubber band, right? It is invariant to deformation. So one example of topological descriptor is the Euler number, which is defined as the number of connected components minus the number of holes in the region. The Euler number is invariant to translation, rotation and scaling. The Euler number can be computed using connected component labeling algorithms. So Euler number E is equal to C minus H, where C is the number of connected components and H is the number of holes in the region. For example, say for this figure, the number of connected components or the number of objects is 1. So E is equal to connected component or object, that is 1, minus the number of holes. So there is one hole in this object. Okay, so hole is also 1. So it will come out to be 0. Similarly, for this B, the number of connected component C or object is 1 minus the number of holes is 1 and 2, which is equal to minus 1. And also for polygonal networks, the Euler formula is given by E is equal to V minus Q plus F, where V is the number of vertices of the polygon, that is the number of corners of the polygon, Q is the number of edges of the polygon, and F is the number of faces of the polygon. Okay, so for this particular figure, these are the vertices, this and this one. These are the edges, these lines. This is the face, which is shown with gray color, and these are the holes, 1, 2 and 3, the white colored holes. So E is equal to V, that is the number of vertices. The number of vertices are 1, 2, 3, 4, 5, 6 and 7. So 7 vertices minus Q, that is the number of edges. So Q is 11 plus F, that is the number of faces. So here the number of faces is 1 and 2, the gray color shaded area. So plus 2. So 7 minus 11, which is equal to minus 4 plus 2 will give minus 2. And even we can calculate like this, that Euler number E is equal to number of connected components minus holes. Okay, so here a single object is there, that is connected component is 1 minus the number of holes are 1, 2 and 3, the white portion, right? 1 minus 3, which will also give minus 2. So we can find the Euler number by both the equations. I hope it is clear. The third and last type of regional descriptor is the textures. In image processing, every digital image composed of repeated elements is called a texture, and textures can be very valuable when describing objects. For example, this image shows a smooth texture. We can see that the area is smooth. This image shows coarse texture where there are very minute variations, and this third image shows regular texture where there are regular vertical lines in the image. So there are three main approaches for describing and analyzing textures in digital images. First one is statistical texture descriptors, in which there is histogram based approach, and this approach involves analyzing the distribution of pixels intensities within the image. The histogram of pixel values can reveal information about the texture's brightness and contrast. Second one is co-occurrence based texture. This method focuses on spatial relationships between pixels. Statistical moments such as mean, variance, skewness, etc., uniformity, entropy and other statistical measures are calculated to describe texture properties. Co-occurrence matrices are often used to quantify pixel relationships at various distances and angles within the image. Second approach is structural texture descriptor. The structural texture descriptor deals with the arrangement and organization of image primitives such as lines, edges or patterns, and these descriptors aim to capture the underlying structure of the texture. For example, describing a texture based on presence of regularly spaced parallel lines or grids is one way to use structural descriptors. These descriptors often involve detecting repeating patterns and quantifying their orientation, spacing and regularity. And third approach is spectral texture descriptor. Spectral texture descriptors involve the use of frequency domain analysis, often employing techniques like Fourier transform. They focus on the frequency components within the image to describe its texture properties. By transforming an image into frequency domain, one can examine the dominant spatial frequencies present in the texture. This can reveal information about the texture's periodicity, orientation and scale. And see, each of these approaches has its own advantages and is suited to different type of textures and applications. Choosing the right texture descriptor depends on the specific problem and the characteristics of the textures you want to analyze. In practice, a combination of these these approaches may be used to provide a more comprehensive description of the texture within digital images, allowing for better object recognition, classification, and image understanding. Let us implement simple regional descriptors, topological descriptors, and textures in MATLAB. And with this, we complete our chapter on image representation and description. You can find the lecture notes or PPT in the Google Drive link that is shared in the description box. Also, the MATLAB codes can be found in the description box. Thank you very much.